Putting a complex machine like the Apple-1 back to work without knowing what condition it's in requires special care. In order to preserve its historical value and its state of preservation, it was agreed to avoid or limit invasive interventions as much as possible. Special care was given to its power supply unit, focusing in particular on components subject to aging and malfunction. Initially, we looked for signs of aging, like swelling, by carrying out an accurate visual inspection, especially on the capacitors, which are the blue cylinders you can see on screen, involved in supplying power, rectifying and stabilizing current. The large heat sink for the integrated 5-volt stabilizer circuit wasn't fastened properly. This could have led to problems on the 5-volt lines. A quantity of dust and dirt was removed from areas close to the power unit. We noticed a video signal level calibration trimmer was missing, replaced by a bridge set to the maximum output level. No other major problems were found. To safely test the power supply unit, which could not be separated from the logic board, all integrated circuits were removed. Anti-static bracelets and appropriate tools were used to avoid damaging the integrated circuits. These were then stored in an anti-static container. Many of the integrated circuit's pins showed signs of superficial oxidation. Unfortunately, we realized the sockets were not high quality. Once the integrated circuits had been removed, we were able to test the power supply unit. 8 rectification diodes were checked, 4 for each supply input section. We then checked the resistance of the capacitors set between the rectification and stabilization stages to see if any single capacitor was short-circuiting or electrically open. None of the capacitors showed signs of malfunctioning, and the growing resistance levels at each measurement seemed to imply they were charging up. We then charged each capacitor, gradually increasing voltage until they reached nominal levels, checking they didn't short-circuit and that they didn't absorb unusual quantities of current as they charged. The following step was to check the integrated voltage stabilizer circuits set to supply 5 volts, minus 5 volts, plus 12 volts, minus 12 volts. First of all, the 5-volt stage was checked, the most important because of the amount of power it has to supply. Instead of feeding the stage with alternate current supplied by external transformers, we decided to feed it with direct current with a lab-grade stabilized power supply. This allowed us to monitor and limit the maximum level of absorbed current and to gradually and slowly increase voltage until we reached nominal values. The 5-volt regulator appeared to be in excellent working conditions when running on empty. To test its behavior under stress, we connected a load resistance to the 5-volt line, able to absorb approximately 1 ampere. Once we'd tested performance and stability under stress, we declared the stage to be in good working conditions. The same procedure was also applied to other power supply stages. In this case too, no major problems were found. Voltages were all within tolerance levels. We then started checking the feeds on each of the integrated circuit sockets. In addition to multimeter readings, we also connected a small light bulb to put a slight load on the power supply unit and the line being tested. The load acted as an indicator of damaged or broken soldering, as well as of the state of oxidation of the sockets themselves. High impedance multimeter readings could detect the correct voltage, but not problems occurring under stress, which would have been hard to identify later. All voltages, 5 volt, 12 volt, minus 12 volt, minus 5 volt, were correctly detected where they were supposed to be. At first, I was more concerned about what was happening with the Apple-1. But I later realized I became involved with a group, with these guys between 35 and 70 years old, who were as excited as I was, but were living this experience with a level of knowledge I found truly fascinating. So I enjoyed their company more than I enjoyed the Apple-1. It was also great to share in the feeling of success and satisfaction that ensued when it was switched on and it greeted the Polytechnic. This stage consisted of reinserting all the integrated circuits that had been removed. We decided not to chemically treat the sockets and the circuits, as the chemicals might damage the logic board's printed circuits. The integrated circuit pins were brushed to delicately remove impurities deposited over time. The pins were straightened with a special tool to minimize the mechanical pressure needed to reinsert the circuits in their sockets. The position of the integrated circuits on the printed circuit board was checked many times and by different people to avoid possible mistakes. Before connecting a keyboard and a monitor, we checked for key signals with an oscilloscope after appropriately calibrating our probes. We then connected all the necessary power cables to our lab-grade power units and connected the probes to the main oscillator and the composite video output. Finally, we switched on the power. At first 24-26 volts with a dual feeder in tracking mode, and then 10 volts. The oscillator worked right away, the frequency was within the appropriate range, but the composite video output did not show any waveform related to a video signal. We thought of bootstrap problems, that is, the prompt was not loading the initial program, so the video was not being initialized. By probing data buses and the microprocessor, we learned that a part of the addresses was never used, which seemed to confirm our initial diagnosis. So we temporarily connected a keyboard featuring a reset button acting directly on the microprocessor's pin to try and reset it. Once we'd verified that the signal reached the appropriate pin, we were able to ascertain that all the data and address buses were showing signs of activity. But the video signal was still missing, so we looked at the final stage of the video amplification process carried out by an NPN transistor. Preliminary inspections had shown that in the past someone had carried out some work on this section and the trimmer had been removed. An accurate inspection brought to light a small splash of solder between two of the transistor's connections. It was removed, but after rebooting, the video signal was still missing. By testing the transistor's legs, we ascertained that the base was at 5 volts, that is, a voltage value incompatible with the requested function. Thinking the transistor might be broken, we removed it, but a test revealed it was working. Not only, it was incompatible with the logic board's pins, which requested a central base, while the transistor we removed had it on the side. Surprised by this discovery, we replaced the transistor with a compatible model. We connected a TTL keyboard taken from an Apple-2 through a cross-connection board that could provide the signals required by the Apple-1. We then powered the computer again and obtained a very promising waveform on the oscilloscope that looked like a video signal. We then connected a composite video monitor compatible with NTSC to its connector. With the monitor connected and switched on, we could see a series of flashing @ and / symbols, which meant the machine's bootstrap had been successful and that the video was working. At this point, we reset the machine and cleaned the screen with a clear screen button on cross-connection board between the Apple-2 keyboard and the Apple-1 logic board. The backslash prompt showed the machine was ready. Apple-1 doesn't have a PROM resident environment or basic interpreter, but just a small program called Hex Monitor, which allows the user to inspect, write and run programs from memory. So we keyed in a small program to visualize the entire ASCII character table. The computer's full functionality was confirmed by successfully running this program. After becoming familiar with the commands and programs included in Hex Monitor, we tried to load the BASIC environment. Originally, BASIC came on audio cassettes. An everyday cassette player was connected to Apple-1's appropriate interface, and through Hex Monitor it was possible to save one's own programs or load ready-made programs. We didn't have a cassette player, but we had the original sound file, so we connected the input cassette interface to the headphone output of a modern computer. The major prompt means we're inside the basic environment, and that we can start programming in this language. We then try to write and run simple programs to visualize words on screen. My name is Claudio Parmigiani. I work in telecommunications and I was involved in this project because I told Marco Boglione an Apple-1 was going to be up for auction at Christie's. My name is Gabriele Celeri. I teach at Milan's Feltrinelli Institute, and I was involved because I've learned to spot possible causes of malfunction on electronic devices, also just by using my eyes with a visual examination, and I have a lot of experience in dealing with electronic circuitry. My name's Gianfranco Albis. I've worked at Turin Polytechnic for more or less 20 years. I run training workshops and I was involved in the project as an expert in old-school electronics. Working in 2011 on a machine built in 1976 means you need to move very carefully. There are many components that may have deteriorated over time, they aren't easy to find, and you have to be sure not to add further damage to that caused by aging. It should be said that circuits in 1976 were a lot simpler than those currently in use. Nevertheless, this simplicity could conceal pitfalls which could be hard to come out of. So all in all, managing to get a machine like this back into working conditions is quite an achievement, both from a technical and a personal point of view. We tried to keep it as simple as possible, and we were successful. We managed to find 2 or 3 actual faults quite quickly. As we worked, I too felt very dubious at times, but this was due to what I didn't know about the machine's previous life. I didn't know who the owner had been, if he'd been an amateur, a professional, or as they call them today, a hacker. These were all variables that could in some way jeopardize the machine's working performance. Let's imagine we've found out that a 1976 component was broken. What are the possibilities of finding a component from those days on the market? Realistically, they're quite limited. The problem we faced before starting to work on the machine was to put together a certain number of components that we could use to replace any broken ones we might have found on the board. In the past, I've also worked on high-range scientific instruments, not only computers, but their price range was absolutely inferior. To work on a machine knowing its price of purchase made me quite nervous and scared of damaging it. Like any enthusiast, we gathered in our drawers layers and layers of circuits and components from those years. Most components are standard, so they're still in production and available today. So many were produced, and components have always belonged to the same class, so there's a certain degree of interchangeability between them. This applies especially to microprocessors, RAM memories, etc. With a bit of luck, we managed to find all the parts that could cause the machine to experience critical problems. We had a number of spares we could use as replacements if necessary without altering the machine's production date. Because if a machine is built with 1971 components and I replace them with parts made in 1990, this is not appropriate for the machine. But if I replace a part with a component from the same time, it's as if the repair had occurred back in the past. Before the Apple-1, computers didn't necessarily have a keyboard or a monitor. After the Apple-1, they all did. So that's the meaning. Change. They laid the foundations for 40 years of computer revolution. The meaning of switching back on a machine like this is also about taking a plunge in the past, remembering when we were young and we carried out the first experiments without having any possibility at all of imagining what future technology would be like. When we worked with machines like that, we felt we had state-of-the-art technology in our hands. My first computer was a VIC-20 bought around 1982 when I first started working at the Polytechnic. There were outdated machines which had been extremely innovative, like digital terminals, the VT100 and VT200, and personal computers were IBMs. I remember we'd bought some computers for the lab, and at the time a normal IBM computer, maybe a bit better than standard models, would cost 10 million lira. My first computer was a small portable Casio. It was 1983 and it could be programmed in BASIC. I still have it and I occasionally still switch it on with great pleasure. And it had, just imagine, a little less than 1.5 kilobytes of RAM memory. In 1980, a famous magazine of the time published a plan for a small home computer. This stimulated my imagination and I built it. This machine, which at the time took up 3 cubic meters in my flat, managed nonetheless to handle all the building's expenses without problems. When I heard Boglione had bought such a rare machine, I thought the operation was interesting, first of all from a historical point of view, because he salvaged a machine that marked the beginning of an era. From the point of view of its cost, let's just say it was substantial. Certainly not within everybody's range. Maybe it could have been bought by a museum or an institute of some kind. What left me a little puzzled was the fact that a private citizen had bought a machine like that at such a cost. I bought the Apple-1 because IT is something I'm passionate about. And as someone once said, the only difference between men and boys is the price of their toys. During my life, I've thought about this machine a lot, because to me it's a milestone, and something very important happened because of this machine. Personally, I think it changed the world. Well, it was certainly quite exciting, also because we couldn't take for granted that it would work. We found some exceptional people, and I'd like to thank them from the bottom of my heart, thanks to that wonderful place called Turin Polytechnic. Thanks to their amazing enthusiasm and level of skill, the machine was fully tested following original protocols. Later it was switched on and it started working, just doing its job. Its own language was loaded and, what a coincidence, that language is called BASIC, and with a modern-day device built by the same manufacturer, which is Apple.
Un oggetto di ultima generazione della stessa casa produttrice che è la Apple.
Well, there are always lots of future projects. Who knows, maybe also a project which has been discussed many times, which is creating in Turin a user-friendly facility for ongoing cultural research based on entertainment dedicated to this new information technology phenomenon. I say new because it's now widely available and because it's only 30 to 35 years old. It's not something ancient, but it's achieved an extraordinary level of social relevance worldwide.
Straordinario.